I'm Chris Fields, and I'll be presenting this course in 6 sessions. And Andrew will be organizing discussion sessions after each of those. And all of this is explained on the course website. So let's start. This is a course on physics as information processing. And this first session will be a historical perspective on the idea that physics is or is about information processing. And I'll just start with a few quotations that span the middle of the 20th century from Wittgenstein in 1920, saying the world is all that is the case, so defining the world in terms of facts, not objects. Landauer in the early 60s proclaiming that information is physical. And then John Archibald Wheeler, who in many ways is the grandfather of this era recently, stating it is it from bit. So things come from information, i.e. bit strings. And if nothing else, this shows that formulations of this idea get pithier as the 20th century rolls on. But the history goes back farther, clearly, than the 20th century. But I'm only going to really talk about a piece of it. And the timeline that I'll actually discuss today, the most relevant history of this idea, goes back to the mid-19th century. And the first specific thing I'll talk about is Clausius's definition of entropy. But with the beginning of the understanding of thermodynamics and the role of information in thermodynamics, you get this very interesting multidisciplinary progression of ideas that incorporates the beginning of quantum theory. And the beginning of quantum theory can kind of be dated to the first Solvay conference in 1928 and the famous debate between Bohr and Einstein over whether quantum theory is about knowledge, information, or objects, things. But it incorporates a lot of work in computer science and logic and mathematics. So interestingly, computer science was born effectively in the mid-30s with the work of Church and Turing, which very rapidly converged with the work in physics. So today we'll be talking about both computer science and physics. And then in the second half of the 20th century, this just exploded into a huge area. And in consequence of that mid-20th century development, we're beginning to see a new idea about physics, which is roughly encapsulated in quantum information theory. And the new idea is this. It's that what physics is actually about is information transfer across boundaries. And the information, we can represent the information transfer like this, and this is a convention I'll use. A boundary is always a blue ellipse. And the agents that are exchanging information across this boundary are conventionally called Alice and Bob, which is just a more polite way of saying A and B. And when you think about this picture, it becomes clear that what physics is really about is communication. And this is a wild redescription of the idea of what physics is compared to the ideas of Newton or Laplace or even the 19th century ideas. And it's very different from the idea that's been preserved in 20th century physics in the lineage of Einstein and others who viewed classical physics as, in a sense, a fundamental, either as completely fundamental or as a fundamental adjunct to quantum theory. So this way of thinking about physics is a very deeply quantum theoretic way of thinking about physics. And where we're going in this course today is really the how did this all happen? It's the origin story. And about 15 years after Clausius proposed it, Boltzmann had the key insight, which is that entropy is a measurement of our uncertainty about the state the system is in. And in particular, he again, of course, went to formalism and said the entropy, S, is equal to some constant times the number of states that the system can be in that look the same to us. And since that number of states is enormous, the way to make that manageable is to take the log of the number of states. So the natural log is ln. And this constant, k, is called Boltzmann's constant. And Boltzmann was able to do this because he subscribed to a radical and very unpopular theory that material things, including gases like air, were made of atoms, and heat made the atoms move around. And as you increase the amount of heat, the atoms can move in many different ways. So the number of states that they can be in that look the same to us increases. And that's what entropy is. It's this increase in the number of states that the system can be in that all look the same to us with the measurements that we can make. And since they look the same to us, we're uncertain about exactly what state they're in. So entropy is a measure of uncertainty. This was really the beginning of modern physics, because what it says now is that decreasing uncertainty requires energy. It links a measurement of uncertainty to a measurement of energy. And if you think about the uncertainty principle in quantum theory, the core idea of the uncertainty principle is you can't measure a system without disturbing it. So to actually act on a system requires energy, and that's what you have to do to get information. So here's Boltzmann basically inventing quantum theory. So we're going to fast forward by another 15 years to 1900. And in 1900, Planck solved this problem called the black body radiation problem, which was basically how much heat does your hot boiler give off into the air. And all of the measurements of the heat that hot boilers gave off to the air ran into problems in classical physics and caused contradictions and quantities that went to infinity, and all of that was bad. So many people were trying to solve this problem, and Planck solved it by making a simple postulate. He said the energy of the radiation is proportional to its frequency, so its color in the case of light. And if you go higher frequency, you end up in ultraviolet and X-rays and gamma rays. If you go to lower frequency, you go into microwaves and radio and all of that. So this is a nice way of talking about radiation. And it turned out that this solved the problem. I mean, just assuming this simple proportionality relationship produced spectra for black body radiation that worked, that matched what you saw experimentally. Well, this means something very important. It means because this number h, the proportionality constant called Planck's constant, is a number, it's finite, it means that energy comes in discrete units of h. You can have 1h or 2h or 10 million h, but you can't have half an h of energy. So it's quantized. And this is widely recognized as the birth of quantum theory. But of course, we should have known this already if we just thought a little bit, right? We know that changes of energy are proportional to changes in entropy by temperature. And we know that entropy is a measure of the number of states, and numbers of states are just numbers. You can have 1 state, 2 states, 3 states, 10 million states, 100 billion states, but they're all just a number. 1 up. And it's not infinite. There's not an infinite number of states unless you have an infinite amount of energy, which we don't have. So we knew already that entropy could only take discrete values. And since energy and entropy are basically the same thing, we knew already that energy could only take discrete values. So we could have realized in 1900 that energy is quantized because the number of states is quantized. So it shouldn't have really been a mystery why energy was quantized, but it was a mystery. And it stayed a mystery. It's still a mystery. People still debate the meaning of quantum theory. But another thing we could have known in 1900 was something very important. And it's that this quantum of action, Planck's constant, which has units of action, which is energy times time, is intimately related to Boltzmann's constant. And Boltzmann's constant has units of energy over temperature. But this wasn't actually understood until the 1950s. No one really figured this out. There was this relation until the 1950s. And when it was figured out by a guy named Giancarlo Wick. And he introduced this notion of the Wick rotation by realizing that if you have an equation in classical physics, and in it there's the term 1 over kT, you can always replace that 1 over kT with this other expression, IT over h bar. H bar is just h divided by 2 pi. And you'll get an equation that's valid in quantum theory. And this is typically described in textbooks as a trick. And whenever something in physics is described as a trick, what that really means is it's something we don't understand. And lots of papers have been written about the meaning of the Wick rotation. But to start to understand the Wick rotation, I want to look at this equation a little bit. 1 over kT is 1 over an energy, and IT over h bar is 1 over an energy, since h bar is units of energy times time. We have time in this equation. And then we have this factor I, which is typically thought of as just an imaginary number. So it's the square root of -1. And what's this I doing in this equation? And in fact, you see factors of IT over h bar, if you're familiar with quantum theory, everywhere in quantum theory. So what's the meaning of this imaginary number? And if you just think of IT or of I as this arbitrary imaginary number that somehow renders the equation mysterious, then the whole of quantum theory is mysterious, but the Wick rotation is very mysterious. But what I is actually is an operator. And if you think of the real numbers as an axis, which is always drawn horizontally, so here it is. Here's 0, and the axis is pointing that way. I'm sorry, I can't get the camera really far enough away to see my arm here. So what is I? I is actually an operator that rotates the whole real axis by 90 degrees. So if you see a plot of complex numbers, then the real numbers go this way and the quote imaginary numbers go that way. So what multiplying by I has done is rotate by 90 degrees. And of course, if you do I squared, you rotate twice by 90 degrees. My arm won't do this, but you end up pointing that way. And those are the negative numbers. So I is an operator that rotates something by 90 degrees. And if you rotate 4 times by 90 degrees, you're back to the identity. So I to the 4th is 1.